So I will start with a brief summary of what we did last week, and then today I'm going to talk more about applications, and next week also, to biological data, and try to see whether when we train a machine on biological data, so on protein data, on neuroscience data, which are the main two applications I'm going to talk about, what this machine mean. Okay, so that is what do they mean, and what can they tell us or teach us about the underlying biological problem. Okay, so briefly what we talked about last week was this kind of machine, restricted Boltzmann machines. So we arrived at this kind of architecture through different steps, through autoencoders, through PCA first, then through autoencoders and so on. And just to remind you briefly how the machine works, this is just a particular example of a Boltzmann machine, or an Ising or Potts model if you prefer. And the peculiarity is that some variables, some nodes in the networks are actually hidden nodes. So we don't have any values for these nodes from the data. So we have to guess the values in order to match the data as closely as possible. So, okay. So the machine, just as a summary, is sampling two sets of configurations, two configurations at the same time. So the visible configuration on which the data are presented, and another layer of units, which is called the representation layer. And we can write the joint distribution for V and H, where V and H are the two configurations of visible and hidden nodes, as a Boltzmann distribution where the energy is given by this formula, where you see some local potential acting on the visible units, local potential on the hidden units, and couplings in between. And the machine is trained by maximizing the likelihood of the data. We assume the data items to be uncorrelated to each other, which obviously is just an approximation, which can actually be pretty bad on some application, but we can talk about that later on. And the marginal distribution over the visible configuration is simply the integral over H of P of VH that defines some effective energy. So as I said, in one specific case, actually, this machine is giving back the standard Ising model when the V's are 0, 1 spins, so let's say 0, 1 variables, so discrete variables. And this is when the potential acting on the, this is when the potential acting on the visible, on the hidden units is a quadratic potential, this U of H. And the reason for that is very simple. You can understand that if you want to compute the marginal distribution, then this marginal distribution here, which is integral over H of P of VH, is simply, this integral is simply a Gaussian integral. It can be done very easily. And what we get is an effective coupling, or let's say effective couplings between the visible units here, which are quadratic couplings. And this is basically a way to, or a reformulation of a Hopfield model, where the Wi mu correspond to the patterns of the Hopfield model. So we talked about that last week. Okay, so we see that in this particular case, the RBM is equivalent to a model where we have effective couplings in between the visible units. So it corresponds to a different way of thinking about the structure of the data. In this setting here, we want to explain the possible correlation in between the visible unit here through a priori unknown common inputs, and we want to find the best common inputs which can explain the correlation we see. While here we fit the correlation through a matrix of effective interactions, statistical interactions, which can reproduce the statistics of the data. So one thing I would like to say is that even if the machine is not a quadratic machine here, okay, then if U of H is not H squared, then we can in fact effectively define couplings from the RBM. And the way we can do that is the following. So the machine defines a probability of V, which is the marginal, okay? And what we can do is take, for instance, a particular configuration, which I call V0, which is a set of n spins, so V0, 1, or let's say maybe put the subscript here as a superscript, it's better, V2, 0, and so on. So in the case of protein, that would correspond to some kind of things that people call the Y-type sequence, so one reference configuration. And then I can do a change. For instance, these numbers here can be 0, 1, if I'm talking about the Ising model. And I can do one change. For instance, I will change V0 I. So the new configuration V0I is simply the one where I have flipped the spin number I here. I can do the same thing on a different spin. So now I'm flipping spin number j. Okay? And I can flip both at the same time, right? So this is V0ij. Now what I can do is compare the different probabilities of these 4 different configurations, and then that will define some kind of effective couplings, which depends on the background sequence here. So for instance, I can compute some ratio here, which is P of V0ij, where the double change has been done, multiply by P of V0 and divide by the 2 probabilities here. So these probabilities can be estimated numerically by the machine once the machine is trained. And the log of this thing here is actually giving the log of this ratio, is giving me some effective couplings between the two spins, which depends on the sequence V0. Okay? So if I sample over V0, I will get some kind of effective couplings over the whole distribution. So in the case of an Ising model, you can see that this thing actually does not depend on the on V0, simply because there is no higher order couplings. Okay? So I will show you some results about that later on. Okay, so I'm going to talk today about this kind of machine, which is just a particular case of this one, because they've been used a lot in fitting experimental data, and I would like to focus on two particular questions. So three. First of all, how do we train the machine here to get the Jij from the data? So I will show some practical way of doing that. And then I will try to answer the question, what do the Jij mean? Do they tell us something interesting about the data? And then, are these models generative? So that means that once we have trained this machine here, can we generate new data, and do they have actually good properties? Okay, so, and then we'll talk about what good means. Okay, so, let me see. Okay. So what is the first training algorithm? So that's an algorithm which is actually was introduced a long time ago, which is well known, Boltzmann machine learning, and it was strongly inspired from Hebbian learning I talked about in the first lectures. So how does that work? So it's a very simple algorithm, which is basically amounts to massive Monte Carlo simulations. So what you can do is, so what we want to fit from data is the model where now the parameters are the Jij. So essentially, this is the thing. We want to fit some distribution, which is an Ising distribution. Where the VIs are 0, 1s, or plus or minus 1. And we want to find these parameters from the data. So how does that work? There are obviously different ways of doing that, but essentially what we want to do is to find Jij on V such that the lower order statistics of P of V, which depends on the J and the H's, will match one of the data. So what we want to do is actually find J and H such that if I compute, for instance, the average value of Vi on the distribution P here, which depends on J and H, then this will match the value of Vi computed on the data. So I assume I have some data which allow me to compute this first moment here, and then I would like to be able to compute this, and they should match. And this should be true for all i's. And the same thing should be true also for lower order statistics for the second moment, for all pairs Vi Vj. Okay, so the number of equations I want to solve is actually n plus n times n minus 1 over 2, which is the same number as the number of parameters. So I'll talk about the existence of solution in a while. But essentially, this is a problem. So how this problem was first solved in this paper about more than 30 years ago Well, if you have no idea, maybe you can have some good idea about the Gij or Hi or whatever. So start from random Gij and Hi if you don't. Then, of course, what we need to do is to compute these statistics here from the distribution. So I'm sorry, the notation has sigmas here instead of v, but this is obviously the same thing. So that can be done using Monte Carlo simulation. So we have a first problem here about the, it's hard to estimate, for instance, the mixing time or the convergence time in Monte Carlo. So this is very much empirical. So once this is known, then you can compare the left-hand side here to the right-hand side. And most likely they won't match, okay? And what you do then is to update the values of parameters, Jij and Hk, according to this quantity here. So Cij is this quantity here, and the Mk is this one here in the equation I've written on the slide, okay? So essentially what we do is just, you see, for instance, if you find with your Monte Carlo that the correlation sigma I, sigma j is too large compared to the target value coming from the data, then you will decrease the coupling Jij, which is very much intuitive, okay? And same thing for the fields. So there are many, so it's a very nice algorithm because it's a very simple one. So it's guaranteed to converge in principle, but maybe very slow because the thermalization time may be extremely large. So why is it guaranteed to converge? It's guaranteed to converge because actually it can be shown that this algorithm is essentially minimizing a quantity which is called the cross entropy. So suppose my data come as a bunch of configurations, which I call sigma. So these are the V1, VB, where B is the number of configurations, which I assume to be drawn independently from each other. So I can define a quantity which is called the cross entropy here, which is a function only on the parameters J and H, which is the sum of all configuration, data configuration of minus the log of the probability. Okay, so it looks like very much an entropy. Okay, except that I'm using the model distribution here. Log of 1 over p is a kind of, in Shannon terms, it's a kind of information. So when you have an event coming with some probability p, then you can consider how much information it gives me, okay? And log of 1 over p is a measure of this information, very informally here. So that can be stated in a much more formal way. So, but the fact is that I'm using here the probability of the model to estimate this information I'm getting when I see this configuration. And then I'm averaging here, I'm summing over configuration which are coming from my data, and a priori the two distributions are different. So it's not an entropy, it's a cross entropy. Obviously what we would like is actually to make these two distributions match as well as possible. So our goal is to make this cross entropy become an entropy at the end of the game. Okay, so this cross entropy depends on the parameters J and H, and it will have some kind of shape here, some kind of representative curve as a function of J and H. And the important thing is that it's easy to show that it's a convex function, which I will just show in a minute on the next slide. It's a convex function. It has a single minimum, which may be at infinity if J and H, if we have some zero modes here. I'll come back to that in a while. And essentially, when we apply this algorithm here, you can see that these equations are just the same equation as you would have if you wanted to descend. It's just a descent of the gradient, okay? So it's a convex function, you are descending the gradient. So if the learning rate A here is small enough, in principle you should reach the minimum. So it can be very slow. So just one remark I would like to make is that it is true that the algorithm is minimizing S as a function of J and H. So among all the possible Ising models here, you want to find the one which is minimizing the cross entropy. But actually, this minimum here can be also seen as a maximum over all possible models which satisfy this set of inequalities of the entropy. So let me state that again because I think it's interesting to understand that. If I look at the class of all Ising models, okay, and I'm looking at the one which actually matches these first moments and second moments with the values of the data, then this is the model which minimizes the cross entropy. Okay? And you can see that from here. You see, if I differentiate S dagger with respect to hi, for instance, I will see that the derivative of log of z over hi is equal to mi. And this is essentially, this is exactly vi, the average value of vi. Okay? And same thing if you differentiate with respect to jij. But at the same time, you can ask a different question, and this is a very general setting for inferring models from data. You can say, okay, now what I would like to find is a model which actually is able to reproduce some lower order statistics of data, because you believe or you know for some good reasons that actually these are the important features in your data. So we can talk about whether this is true or not. So I'll come back to this point. And the question is, what kind of distribution satisfy these kind of constraints? There are obviously many, many distributions, P of V, which can satisfy this set of constraints. And now you ask, what is the one with the maximum entropy, which is supposed to be the least constrained distribution in terms of information theory, and the one which maximizes this, the entropy under this constraint is the IZ model, which satisfies these constraints here, and this is the maximum of S of P in terms of Shannon entropy here. And both things match. So the maximum of S of P and the minimum of S dagger, they match, and they are the object we want to find. Okay. So why is it a convex function? Well, it's something which is well known. So you can compute the second derivative of this function here, and it will be some kind of big susceptibility matrix, where usually we usually work this thing here, because usually we compute susceptibilities with respect to local fields. You know, how does the magnetization of a spin changes when I change the fields applied on another one? But in fact, you can do that with higher order couplings, not only fields but couplings, and so you get higher order susceptibility matrices. But the important thing is that the quadratic form, which can be built from the Hessian matrix of S, is positive. Okay, so it's a convex function. So it's a well-known fact, I think. Obviously, it is positive. Well, it's a non-negative, let's say, but there could be some zero modes in this susceptibility matrix. So the zero modes are bad in the sense that the minimum here will be at infinity. So this is not only an academic question, an academic issue that may happen. So for instance, if you have, just to give you an example, so that's a trivial example, but so suppose for instance you have a model with a single spin, okay? So you have only one V, which may be 0, 1. And suppose you actually draw some samples, that means configuration of this single spin here, and from a distribution where the probability of V will be a exponential h V, and I normalize here, okay? Where h is the ground truth value over here. Now, if h is very much negative, for instance, then p of 0 will be much larger than p of 1. Okay? So you can have p of 0, which is, let's say, 1 minus epsilon, where epsilon, log h is giving you epsilon anyway, or log epsilon is giving you h, sorry. And p1 will be epsilon, okay? Now, if the number of configuration you have is smaller than 1 over epsilon, you will see always 0. So that means that the value of h which fits better your data is h equal to minus infinity. So the minimum will be at infinity, okay? And obviously that in real data, that doesn't happen on single point function, but on 2-point function that happens a lot. Simply because it's when you have, for instance, value of neurons activities which are likely to be more silent than active, okay? So that means we are in a situation like that here. And the probability of seeing 2 neurons active in the same time is very low. So many of the couplings you would infer are minus infinity. Okay, so how do we prevent these things from happening? We can use some kind of regularization tricks. So there are many ways to do that. And maybe the simplest way is to add some prior on the parameters. So for instance, we want to minimize this cross entropy here plus some penalty which prevents the coupling from being too large. Okay, so I'll come back to this later. But that doesn't change. The important thing is that the penalty which is added does not remove the property of being convex here, which is very important, because otherwise it would be much harder to minimize this function. Okay. So this is one algorithm. So I would like to talk about another algorithm which has been very popular and used in the applications, at least on proteins. And actually, this is what is used now by people in bioinformatics. And this algorithm is called pseudo-likelihood algorithm. So I guess that some of you may already have heard about that, maybe not everybody. So I would like to explain how it works. So again, our goal is to find some values for the Jij and for the Hi, right? So I will explain how the algorithm works in the case of binary variables. But of course, it can be applied to the case of Potts variables with more than 2 states. It's a bit more complicated computationally, but it's exactly the same principle. So I will explain I'll make a summary of the method here. If you want to get more details, you can go to, it has been explained in detail, and there are some proofs, sufficient proofs under which this algorithm works. And I strongly recommend the paper by Ravi Kumar, Wainwright, and Lafferty, which was published in 2010. I think it's Annals of Probability or something like that. I don't remember it. But anyway, so if you Google, you will find it very easily. And I want to mention that actually this paper is an extension to the case of discrete variable of another paper, which is known under the name of neighborhood selection. So this other paper by Meinshauser and Buhlmann from 2006 presents an algorithm which is called neighborhood selection in the case of continuous variable. And the paper by Ravi Kumar, Wainwright, and Lafferty is an extension to the case of discrete variables. Since I am interested here in discrete variables, I'll talk about this one, okay? But you can have a look at this one also. Okay, so again, I am assuming I have some configuration of the data. So we have data, and the data configuration I will call DIS. So I is the index of the spin variable, so it runs from I to n here, and S is the index of the samples, which run from 1 to p. So in the and basically what I would like to find is to find the Jij. The Jijs and the Hi. So in a, let's say, consistency framework, I will assume that the data are drawn actually from some Ising model. And then the question is, how do we recover the values of the couplings and the parameters from the data? So I'm assuming they have been generated by an Ising model. But of course, the algorithm I'm going to explain can be applied to data, to real data, which certainly have not been generated by an Ising model. But then we lose asymptotic results and so on. So the probability of Di in that case will be some 1 over z times the exponential Di, Dj, Jij, plus some over Hi. Okay, and we would like to find back the parameters. So the idea of pseudo-likelihood is actually a very simple idea. It's the whole goal of this approach is to avoid the computation of z. Z is a very complex quantity, right? Very complex in terms of computational effort you need to compute z, because it requires the sum of an exponential number of configurations, and it's completely intractable. So we will simplify a little bit the problem. And instead of considering the n spins together, we'll consider only one of them, or let's say one at a time, to be more precise. Okay, so consider one site. Okay, so which I would call I. And I'm interested in the conditional probability of the value of the spin on side I given the other ones, the values of the other spins on the other sides. Okay, so the conditional probability for spin number I is very simple to express. So if I call it di again, so this is conditioned to all the other values of the other variables. And since I have a single spin problem, it's a two-level system, then it will depend only on some effective fields. So it's di hi over 1 plus exponential hi, where hi depends on the other spins, right? So with hi equal, well, this is the sum of a local field, hi, the external field, plus the effective field produced by the other spins. So it's the sum of a j, jij, dj. Okay, so the pseudo likelihood of the configuration is defined as the product of the conditional probabilities of the single spins in the configuration. So I define the pseudo likelihood of the d's, of the di's, as the product of the I of the p conditional of I of di given the other ones. Okay, so this is important to realize that this pseudo likelihood is not, so there are a few things to say. I mean, this is not the likelihood. Okay, so it depends on the same number of parameters. So maybe I should be more precise. It depends on the whole interaction matrix, on the whole set of external fields. But the fact is that this has nothing to do with the likelihood. So this is not the likelihood, in the sense that this pseudo likelihood here is not the probability of a d's. So we have lost something, but we have gained another thing, which is actually, this thing is actually easy to compute. Because you see, the partition function I have are single spin partition function, so they are extremely simple to compute. So this is easy to compute. If you give me some configuration, I can compute it very easily. And the inference of the j's, I mean, what I want to say is that the maximization over jij hi is easy. So what do I mean by easy? So there are different things that I mean here. So the first one, which is obvious, is that the different rows of jij are uncoupled. What I mean by uncoupled, I mean that actually we can infer the rows one after the other. Okay, so in fact, if I look at jij, this will be inferred from the maximization. So where do I find jij here? So the jij I will find, so if I look at spin number I here, so I have all the other ones, j, and so on. So there will be a coupling, jij, telling me how the value of a spin j is actually influencing spin I through the effective field here. So jij is appearing here in this product only in the conditional probability of spin I.
So jij is not symmetric?
No, it's not. Exactly. So while if I look at jji, then you get immediately that it comes from p conditional of j. So this algorithm, actually, when you do maximization, won't give you a symmetric matrix, jij. It won't be symmetric. But in fact, this is, okay, obvious. I mean, it's not the real likelihood.
Just because you suppose that GI comes from an IC model, but that one had a symmetric GI.
Yeah, so I have generated, okay, so the statement is that if you generate data from an IC model where everything is well defined, everything is symmetric and so on, then if you have a finite number of data and you do this algorithm and you maximize here, you will get a non-symmetric matrix, okay? But if the number of data is large, and I will tell you just in a while what large means here, then you are guaranteed to find asymptotically a symmetric matrix. But for any finite situation, I mean any realistic situation, it won't be symmetric. So people have also some tricks to make it symmetric, so it can be extremely dirty, like symmetrized by hand at the end. Or it can be a little bit better when you put some prior, which asks the matrix to be as symmetric as possible, maybe by looking at the sum of a jij minus jji squared, and then you put some gamma. But they're all dirty things, right? More or less dirty. Okay. So in practice, how do we do that? Okay, so take the log. So we maximize log of pi. So we maximize 1 over p, sum of the, let's say, s running from 1 to p, of the log of pi. So as I said, the different rows can be, the different i's can be uncoupled. So let's concentrate on a single I. So the log of the p conditional of I, di in my sample s, given the dj's in the same sample S, okay? J is different from I here. So I had written this in the other blackboard, but this is cancelled now. But anyway, the expression is simply 1 over P, sum over S of di of S, hi of S, which depends on the dj's here, minus log of 1 plus, so it's a exponential hi of S. Where again, this thing here is just the effective field, so this is hi plus the sum over j, jij, dj of s. So it's a function of the parameters here, the hi and the jij, which are here and here. So let me compute the gradient of this function with respect to hi, for instance. So this is very easy to do. So if I differentiate with respect to hi, I get a term which is sum over s dis over p. And this is exactly the average value of di in the data. Okay. And what is the other term once I differentiate? Well, this is 1 over p. So let me just write it in details. The sum over s, which are the samples running from 1 to p, of exponential hi of s over 1 plus exponential hi of s. And what is it here? This is actually the average value of di in my single spin problem, right? So this is the di in the model, let's say. But in the model is not the IC model. The model is the single spin problem in the background of the other spins given by the data, because it depends on the other configuration. On the data configuration, okay? So it's a mixture of model and data. And of course, if you differentiate with respect to jij, you find the same thing for dij. So it's easy to show exactly with the same argument I have shown here that the second derivative is the Hessian matrix is actually a positive matrix. So the whole thing can be minimized. The Hessian derivative of this thing is a negative matrix, so the whole pseudo likelihood can be maximized. It's a convex function of the parameters. So it's easy to do. So just a word about regularization. So you see, it's not a maximum entropy method. Because in fact, if we were really maximizing the likelihood as we should do, the sufficient statistics come from the data are the first moments and the second moments. There is nothing else we should care about. It's not the case here. We need the full configurations of the data. Okay? But we can use this information to simplify the problem in some way. So the inference problem becomes easy. Okay, so one word about regularization, because it's an important point. As I said, many parameters can be infinite here. So what people do in practice, instead of considering only the maximizing the pseudo likelihood, you can define some kind of cost function, which will depend on, for psi I, on hi on the jij's, with j different from I, where I is fixed here. So it's going to be minus the log of pseudo likelihood, which I have written here. So this is for psi I. And then you can add some penalty terms, like for instance, gamma 1, sum over j, jij, L1 terms, gamma 2, sum over j, jij squared, whatever you want. And you have also other terms for hi. But as I said, I mean, the regularization usually is much more important for the jij than the hi, for the reason I mentioned before. I mean, there are a lot of moments for the two which are actually equal to 0, and the jij would be minus infinity. Okay, and what we want to do is maximizing this term here with the minus, without the minus, so that is minimizing this cost. Now we have the penalties. Okay, so just one thing is that how do we fix the value of gamma 1 and gamma 2? So gamma 2 prevents the jij's from being too large, so this is important. But for instance, the value of gamma 1 is very important. In many cases, the network we would like to infer is supposed to be sparse or close to being sparse. So what value of gamma 1 should we choose? So this is an issue which is discussed in details in the Ravi Kumar's paper, so you can have a look at it. But just to give you a flavor of what is the correct answer, consider a very simple problem where you have only two spins. Suppose you have two spins. Okay? And I'm assuming that actually they are not interacting together. So the true value of J12 is actually 0. So it's it's a toy model where you have two independent spins. But you have a finite number of configurations. So what is the value of gamma 1 you should choose in order really to realize that J12 is equal to 0 and not something small due to noise? That's the interesting question, right? Okay, so the correlation I will have is going to be small, right? So let me assume, for instance, the correlation is small, so which I call epsilon. So the cost will be a function of J12, and I can approximate it as something like that. So there will be some quadratic form, and the A here is related to this susceptibility matrix, okay? And some J12 minus epsilon squared. And this epsilon in principle should be 0, but due to the fact that I have a finite number of data, it's not 0, it's something small. And essentially, I'm expecting this thing to scale as 1 over square root of p. Plus or minus, okay? Where p is the number of data. So this is the cost coming from this part here. And then I will have the other terms, like, for instance, gamma 1, absolute value of J12. Plus, okay, I'm interested in the case of small j, so this term will not contribute anything compared to this one. Just changing the value of A. It does not matter. Okay, so what is the minimum of that, of this function here? So you see, if I plot this function as a function of J12, so in 0 on one side, I have a slope, which is gamma 1 minus A epsilon. On the other side, this is gamma 1 plus A epsilon. Okay, so if epsilon is small enough, both slopes are positive, and this is the absolute minimum in J12 equal to 0. And this is what I would like to find. So we want gamma 1 minus A epsilon to be positive. So that means that gamma 1 should be larger than epsilon, essentially. So gamma 1 larger than 1 over square root of p should be okay. So we don't want gamma 1 to be too large, because otherwise it would put to 0 real parameters which are interesting. So the minimal value of gamma 1 which makes sense seems to be 1 over square root of p. So we have to be a little bit careful, because in real problems we don't have 2 spins, we have n of them. So when we have n spins, we have to be a little bit careful. We have to see what is the value of epsilon we should consider. So now all epsilon will be of the order plus or minus 1 over square root of p, but actually the most dangerous one is the largest one. Okay? So we have n spins, so we have n times n minus 1 over 2 correlations. And if I do a very crude assumption, which is not true, but I mean, more or less, okay? So you can ask what is the maximum value of epsilon, ij, over all ij's. Then essentially I have n squared over 2 variables. The mean value is 0, the variance is 1 over p. So if they were independent, and they are essentially Gaussianly distributed, this is true, because they are just some, empirical correlations, you would expect this to be equal to square root of 2 log the number of variables you are considering, which is n squared over 2 here, divided by the standard deviation, which is, times the standard deviation, which is 1 over square root of p. Okay. So that means that the gamma 1 we should choose is scaling at square root of log n. I'm sorry, it's not. Okay. A square root of log n over square root of p. And in fact, this is proven in the paper by Ravi Kumar. They really show that. Okay. So it's interesting because it tells you that as you have a large number of data, then p is increasing, gamma 1 is, you have to choose, is going to be down, so that's fine. That means that you have a less stringent penalty, and actually the amount of noise you should reduce is going only like square root of log n, which is a very weak growth as the number of, as the size of the system is growing. Okay, so that means that in principle, if you use this gamma 1, you should be able to detect all the jij's which are above this level here. So they show that, and they explain in great details in their paper how that works. Okay. So now plenty of other algorithms. So we have, for instance, developed algorithms which are based on expansions of the cross entropy in terms of clusters. So I don't want to detail that, but I wanted to show this one because I think it's an interesting one from a mathematical point of view, and also it's very much used in practice. So there are packages on the web, and you can download and use that, and it's very fast. So in the second part, I would like now to use this algorithm and show applications to proteins. So this is just a follow-up of what I did last week. And the question is, when we use this algorithm on infer some couplings, what do they mean? And I would like to show some examples of that. So I have an idea that we can find in sequences some motifs of amino acids which are particularly important for structural, functional, or evolutionary properties of proteins. So let me briefly show you again some slides I've shown before, just to remind you of what is the problem here. Maybe some of you were not present last week. Okay, so what we are interested in is when we have a protein sequence, we would like to understand the properties of a corresponding protein. So, and there are many interesting properties a priori, like the structure. So what kind of three-dimensional fold the protein will acquire in space? How stable is this fold? Are there different conformations, this kind of thing? Another one is beside structure. So actually structure is very strongly important. It's very important in this matter, is function. So what is this protein going to do? What are the enzymatic properties of the protein? How will it cleave or bind or whatever, change the conformation of other proteins or molecules? So in more, let's say, detailed way, what is going to be the activity, the affinity for different substrates, the specificity, what kind of substrates are good or bad for this particular protein, and also evolutionary properties. These proteins these sequences have been evolving over time, over evolutionary time scales for billions of years, and some information about this evolution is encoded in the sequence. And there are also practical application of that. So for instance, if the protein has some function, you would like to be able to understand how this is determined by the sequence and what kind of mutation should be done in order to modify some specific functional properties. Increase the affinity, when you have a fluorescent protein, you would like maybe to change the wavelength of the fluorescence, these kind of things, which are actually done in practice. So what people do when they don't have models, computational models, they do what they call directed evolution. So for instance, they will select, so this is just in vitro selection, they will select interesting proteins. So you start from protein, do random mutations, then select, for instance, if you want it to bind very strongly to a target, put this target in solution, then the protein will bind to it, then wash away the solution, you'll get the good proteins, okay? And then you will, from this protein, generate new sequences with some mutation, and then repeat this process until you get something which has very strong binding affinity, for instance, okay? So this is how proteins are engineered, for instance, in the pharmaceutical industry to get very good properties. So, but here we would like to do something similar, but with models. So people have been modeling sequences for a very long time, especially they have been trying to understand what are the conservation properties. So along the sequence, if you mutate, for instance, some amino acid, then the whole protein will unravel. So the structure is lost forever. So these are very conserved sites. But then if you do mutation on many sites, you will see basically no change in the properties of protein if you measure some typical function. So the question is, what is possible as a mutation? And what is important is that is this property which is called in the field epistasis, which is what we call in physics interactions. In fact, the effect of mutations, when you do two mutations, the effects of the resulting double mutation is not the sum of the effects of each single mutation, okay? Because the two mutations may interact together. And in fact, this is the kind of effect we would like to capture with this GIJ. So how this is done in practice? So we use the fact that, across evolution, the protein coming from the last common ancestor has evolved across many organisms. So what we have now in databases are, let's say, many realization of proteins having essentially the same structure and function to a first approximation. So we get this bunch of sequences here, and we are in essentially the same framework as here, where we get some configuration, DIS, and we would like to find some underlying network of interactions to explain this, the pattern of correlation or of epistasis in the data. So in practice, once the different proteins sequences corresponding to the different organisms are aligned on top of each other, so each line is an organism, or you can have sometimes more copies of a single protein in the same organisms. That may happen also, so it could be the same organism but different parts in the genomes. Then we can compute the first moment, for instance, which is the frequency on each site of the amino acid A. And we can compute the second moment, which is the joint frequency on site I and J of A and B, the corresponding amino acids. Okay, so, and from that you can compute some correlation matrix, or let's say covariance matrix, or normalized correlation. And just to give you an idea, again, I just remind you that the length of a protein runs from tens to hundreds of amino acids. And the number of sequences you find in public databases ranges from hundreds to hundreds of thousands, depending on the particular domains and on particular proteins people have been considering. But you see, as you have hundreds of amino acids, that means the number of pairs here is going to be very large. It's going to be the square of that, so it can be 10 to the 5 easily. And for each pair, you have a 20 by 20 matrix here. So there are huge numbers, which should be estimated from a few thousand of sequences typically. And now people have been interested in finding models with interactions and local fields to describe this sequence statistics. And I've mentioned last week these two papers which were very influential, one by Lapedes in 2001, which was unpublished, another one by Martin and collaborators, Martin Weid and collaborators in 2009, and then there have been many papers in the field. And the reason why there have been so much interest in the field is the following. That's the first reason, is that if you look at the effective couplings which are inferred, and this is something I've shown last week, then the Provenance Norm, for instance, so JIJ-AB is a matrix which depends on the amino acid contents on the pairs IJ. So I can shrink this thing, condense the information into an estimator, a quantity which depends only on the pair IJ, and a simple thing you can do is a Provenance Norm. So for each pair IJ you get a number, which is a positive number, and you can rank these numbers from the top to the smallest one, and then look at whether the corresponding pairs are actually in contact on the structure. The idea is that pairs of amino acids which are in contact together on the fold cannot mutate independently because they have to maintain the contacts, the structure. So there should be some strong couplings in between. So we'll see whether this is actually a good intuition or not. It seems to be a good intuition because on small protein domains like this one, if you look at the top 30 pairs, for instance, they are all contacts, correspond to pairs of amino acids which are within 8 angstroms from each other. And so it's interesting because from sequences alone, you can get a lot of information about the 3D structure of a protein, which is a very nice idea. And this is actually at the basis of the most powerful algorithm for inferring structure right now. Okay, so the question I'm interested in now, the next 30 or 40 minutes, are the following. So to what extent are the inferred statistical pairwise coupling good predictors of contacts of a native structure? So we see that in that particular example, it works well, but I mean, we would like to understand a bit in a more detailed way why this is true and what are the limitations, because the intuition is very hand-waving here. And then there are also questions which are, if you are not a structural biologist, you may be interested about the meaning of a GIJAB. When you get a couplings between two sites, which depends on the amino acids, how do they actually reflect the energetic interaction, the true physical-chemical interactions? Okay, because they are just statistical couplings, but are they related to the physics? And what do they tell us about the underlying protein? I mean, here the intuition is just that it tells us something about the contact map of the protein we are interested in, but this protein is interacting with many other proteins. So how do we see this information in the set of GIJAB? So these are the questions. And then we have another question I'd like to talk about is that can we really take this model seriously and actually use it to generate new sequences, and are they functional sequences? And I will show you some experimental results. Okay, so in order to answer the first question, I will consider very simple models of proteins, which are not real proteins, but they are interesting because they can guide us to understand what is going on also in real proteins. And so the model I will consider are models which were introduced many years ago, and they are what people call lattice-based proteins. So they were very popular in the 90s, at a time where computing power was not so extended. So people could simulate these proteins on discrete geometries. So I'm showing you, so there are many models like that. And so I'm showing you one particular model, which was introduced by Gene Shaklovich and collaborators in the 90s. And here is a very simple example. So imagine you have a protein in this model is a sequence of 8 amino acids. So it's a polymer of length 8, which can fold onto a cube, which is a 2 by 2 by 2 cube. So you have 8 sides, okay? So there are many ways you can actually, put your polymer on this cube so that each amino acid is on the corner, on one of the corners of the cube, one of the vertices of the cube. So I show you 2 different possible folds, which I will call fold or structure. The following, it's the same thing. And of course, all these folds are competing together in the sense that a protein may fold into this one or this one depending on its energy. So how do we define the energy associated to a fold or to a sequence? So this is the core of the model. So given a sequence, we will compute an energy which will depend on the particular fold, the particular conformation of a polymer. So a sequence here is a sequence of amino acids. And the model we use is a very simple model. Is this one. So the energy of a sequence of amino acid A1 up to A8 in structure K, which is one of these possible conformations, will be a sum of pairwise terms. So what we do is you look at your structure, this is one particular structure, and you look at all pairs of amino acids which are in contact. So contact means here neighbors on the cube. So for instance, H and A, okay, the histidine here is in contact with this amino acid here. And so I will have a contribution in the energy which corresponds to a pair factor here, which depends on H and A. So we have a big 20 by 20 matrix, which tells us what is the energy when H and A are close to each other on the cube. So this matrix here is called the Miyazawa-Jerningham matrix, and it was measured by people in biochemistry in the following way. They have a list of structures of proteins which are known, and they know the corresponding sequences. So they look at all amino acids which are in contact, and they look at the frequencies of the different pairs. So you get 20, a matrix of joint frequencies, 20 by 20. And then they essentially compute the log of these frequencies, and that determines some kind of effective energy. That's called a knowledge-based potential. So I'm just making the story a little bit shorter, but this is the idea. This is exactly the idea. Okay? And we are assuming that the total energy will be a sum of pair terms like that, which is obviously an approximation. It's a simplification. Yes?
Just a question. Do you, for instance, C and H are neighbors? They are should with the same way?
Yes. Okay. So I don't put it here, but I mean I could put it here because they are in contact. I don't put it here simply because actually there are always neighbors in all folds. So if I want to compare the energies of the different, that they would just cancel. Okay. But you are right; they should be included. Okay. So we have a sum of the I and J, so which are the pairs of amino acids, a pair of sites. The Cij, which is a matrix telling you, which is equal to 1 if I and J are in contact, or 0 otherwise, times a factor which depends on the amino acids which are carried by the sites. Okay? So it's a very simple model. So for instance here, if I haven't made any mistake, this is, for instance, the two structures with the same sequence, and you can compute the two energies, and you see two different numbers for the same sequence. Okay? Okay, so now how do we know whether this particular sequence, CH, E, I, K, and so on, is falling into this structure, this one, or another one? So for the given sequence, we compute all the energies over all the possible structures, and then we define a Boltzmann distribution for the different structures conditioned to a sequence. So this was called by Shagnovich and collaborators the probability P0 is related to native, but whatever. It's a probability that this particular sequence will fall in this particular structure. And this is the exponential of minus the energy of the sequence with the structure, considered here, over a partition function, which is the sum of all possible structures of the Boltzmann factors. Is it clear? Okay, so I have the only important thing here, so let me maybe write again this thing on the blackboard, because otherwise it will be, I need that. So it's a model where you have actually, it's a bipartite model in some way. And then I will give you numbers in this, shortly give you numbers. So you have sequences. So you have a set of sequences. And a set of structures. So here in my very simple case where I have only 8 sites, the number of sequences here would be 20 to the 8 because I can have 20 amino acids on 8 sites. The number of structures will be something. I will give you some numbers on more interesting, slightly bigger cubes. And for each particular structure and each particular sequence, I have a number which is an energy which depends on the structure and the sequence. Now, if I fix my sequence here, I have many possible energies. And maybe one of them will be much lower than the other ones. Maybe this one. In that case, I will say this particular sequence falls in this particular structure. And the indicator is given by these numbers here. So I want one of these probabilities to be much larger than the other one, maybe equal to 0.999, and all the other ones are very small. Is it clear? So the model is very simple. Okay, so how do we generate, now suppose we want to generate sequences which fall in this particular structure. So what we do, we look at this table here, but in the other way. No, I don't have other colors, but anyway. So, so now I fix a structure which I am interested in, and I call it native structure. And I would like to generate data. That means sequences which actually fall within this structure with very high probability, 0.999. So that what I will do, I would like to scan here all possible sequences and find the ones for which the energy is much lower in this structure than in all the other structures, right? obviously there are too many of them. So what we do is just a Monte Carlo. What was done in the field is a Monte Carlo, and you have an effective Hamiltonian, which is minus the log of this probability here, and you can sample at some effective temperature with this Hamiltonian here. Okay, so essentially you put p naught to some beta inverse temperature, and you will sample configuration according to this thing here. So if this beta effective temperature is very large, inverse temperature is very large, then you will sample only configuration of amino acid which have a very high value of p naught. Okay, and this can be done by Monte Carlo. So in practice, you can generate data with this algorithm. Is it okay? So it's a way to generate data. So we have a multi-sequence alignment corresponding to one particular structure. So I have emulated what you find in real data, where you have proteins or sequences which correspond to one particular structure. Obviously, everything is much simpler here. So one important thing is that for the energy here is a sum of pairwise term. Okay? So if you do not, given a sequence, for a given sequence of structure, you have a sum of pairwise terms. The effective energy from which we sample here is not a sum of pairwise terms, because the different structures are competing together. So this denominator here has higher order terms. So it's an important thing. That means that the true model, which is given by this Hamiltonian here, is not a two-body coupling Potts model. Okay, it's something more complicated. And in fact, in reality, that should be the case. But now we'll use this kind of inference method I've talked about to fit this data and see what it gives. So at best, the model is very effective, right? Okay. So in practice, we don't use a 2 by 2 by 2 cube, but we use a 3 by 3 by 3 cube, which is only marginally better, I think. Shatnovich says that he can do a 4 by 4 by 4, which is just much slower. I'm not sure it's very interesting. But anyway, it's interesting to get better data, larger data, but I don't think it would change a lot what we found. Okay, so what are the numbers here? So now on a 3 by 3 by 3 cube, this is 20 to the 27, so the polymers have length 27. So this is 10 to the 35. Now about 10 to the 35 possible sequences. And the number of structures, they have been enumerated by Shatnovich and Gutin, and they have found about 10 to the 5 structures. That means now about 10 to the 5 different conformations of a polymer on the cube, which are different. Obviously, two conformations which are equivalent through a global rotation or symmetry are considered to be the same. So they are really different. You cannot go from one to the other by a simple transformation, global transformation of a cube. Okay? And you can generate sequences like that. So essentially, the situation is this one. You have this huge sequence space with this number of sequences. There are 10 to the 5 possible structures. And now you can say, let me consider, for instance, the sequences which fall into this conformation with a probability larger than 0.99. That will define a bunch of sequences here, and my Monte Carlo will essentially sample this thing here. And I will extract just a few thousands of sequences or a few hundreds of sequences for that. So the number of sequences here is actually much, much bigger than the size of a multi-sequence alignment. Okay? And now you take this data here, these few hundreds or thousands of sequences here, and you infer your Potts model, and you ask what these things are doing. What do they mean? Is it okay? So it's so first thing, do we find exactly the same result as people find in real data? So can this, if you look at the top, the biggest couplings, do they correspond to the contacts? So not surprisingly, they do. So here is a plot where you can look at the rank of a score, or exactly this Frobenius score, which goes from 1 to 20-something. And here you see the fraction of these top scores which correspond to contacts. And you see when you use this pseudo-likelihood maximization algorithm, inference algorithm I have just explained on the blackboard. You get perfect prediction up to 20-something contacts. Okay. So the largest couplings do correspond to the contacts. So empirically, this is what people find in real data. And this is true. This is for this structure. This is true for other structures. So actually, the point at which this will go down depends on the particular structure. Some structures seems to be harder to predict than others. Okay. Now, let's try to see what this coupling means. So a simple thing we can do, since here we are in a very good situation, since we know everything about the model, we know that here if we look at the energy, not the effective one, not the true one, but the one we use for a given sequence, a given structure, it depends on the structure here and on the physics here. The interaction values are here. So we may ask whether the JIJB we infer looks like the Miyazawa-Jernigan matrix. I mean, do they reflect the values of the true interactions? So the simplest thing we can do is the following. Take one particular structure, generate an alignment of sequences which fall into the structure, compute the JIJB, and now do these kind of things here. You take all the pairs of sites, which are this number, 26 by 27 over 2. You take all pairs of amino acids on the two sides. And now for each of these things here, IJAB, what you can do is look at the value of JIJB you have found in the data. I mean, in the inference here, and plot this with respect to EAB. That means you do some kind of scatter plot. So this is minus EAB versus JIJAB. So you see this kind of things here. So there are 400 values here, a priori, and there are many more here. So you see this kind of cross. And the kind of cross actually takes a lot of sense if you put some colors. And here I put red color for the pairs of site IJ which are in contact on the fold. And I put blue for the ones which are not in contact. So you see a very strong positive correlation in this case, and a small negative correlation when they are not in contact. So it's certainly true that we were expecting this strong correlation, because that's the basis of the whole thing which is done in real data analysis, right? But this one is somewhat interesting. So how can we understand that? Okay, in order to understand that, we can do the following thing. So take a particular structure here and generate many good sequences here. So you sample with the Monte Carlo. And you may ask whether actually how these sequences behave with respect to the other folds, to the other structures here. Certainly they have very low probability of folding into this one, right, by construction. But the question is how low are these low probabilities? And how does it depend on the particular structure? Maybe all these sequences are uniformly bad over all the structures here, or maybe some of them are actually more dangerous than this one. They compete with the native fold. So you can take these sequences in the MSA, in multi-sequence element you have generated, and compute this ratio here. That's some kind of relative weight that tells you what is the ratio between the probability that my sequence which falls into this particular structure with high probability, so this number is high, 0.99, and what is the ratio between this number and the probability that it falls in another structure. So this number will be small. Okay, but for some structures it would be maybe 10 to the minus 4, for the one it would be 10 to the minus 60. Okay, so it gives you some kind of relative importance of the different structures in competition with the one you are interested in. And now what we can do is look at the average competing structure, which is, if I look now at all my other structures, not the one I am interested in, but all the other ones, I can compute the average contact map of the average structure, if you prefer, weighted by the importance of this other structure. Okay? Is it clear here what I'm doing? Okay. So I'm considering all the other ones, and I'm trying to rank them according to this factor here, this coefficient, and that gives me something. So, for instance, for the structure SB I was showing here, I can get the contact map here, which is just a bunch of 1 and 0 depending on the particular contacts. And then I have all the other ones, so there are 2 of them, but actually there are about 10 to the 5 of them, and compute these 10 to the 5 numbers, and compute this other contact map. And this is what you see here. So here you see, so since actually this is a symmetric matrix, I need only I smaller than j or I larger than j to represent the whole matrix, right? So in the lower triangle, you see the Cij matrix for this particular structure SB I mentioned before. So all the blue dots correspond to contacts. So that means, for instance, site number 1 here and 14 are in contact okay, on the structure. Is it okay? And here, all the green dots corresponds to the pairs ij, which are among the top 28 Provenance norms of the inferred couplings. I said 28 because I know that the number of contacts on my structure is 28. And you see many of them match. And this is exactly another way of saying that you get good prediction. But you get a few mistakes. Large couplings which are not contacts. So now, let's look at the other one. That's the C bar ij, which is the average contact map over all the other competitors, but where we put a lot of weights on the ones on the structures where the probability here is not too low compared to the other ones. And you see these kind of things here. And what you see is that these large couplings here actually correspond to some large cores here. Yeah? Obviously, there are other large cores, but some of them were already in contact in this structure, so we don't care. But this one also, these things here, so that means the Cij bar average over all these structures which are in competition were large here. So in most of the other structures, they are in contact, but not in the native fold. So that's the reason. Okay. So essentially, so now I'm going to explain that in more detail. So we can have some kind of approximation for Gij, which is not exact, which is only exact when the gaps is going to is very large. So by gap, I mean this number here, the smallest of these numbers here is actually going to 0. So that means the other structures are very far away from the one we are interested in. And one thing we see is the following expression, approximate expression. So the Gij is proportional to EAB, the Miyazawa-Janigan things, which is what I've shown before in this plot here. And the coefficient of proportionality is proportional to the difference between the contact map on the true structure you are interested in and the difference with the average contact map over the competitors. So if I and j are in contact in the fold you are interested in, this is 1, and this thing is usually small. So you get a positive correlation. If you are not in contact, Cij is 0, and this thing is usually small, so you get essentially 0. But in some cases, Cij bar may be actually not so small, and so you get 0 minus something not so small, so you get a minus thing. And that corresponds to the correlation which is seen here. So what does that mean? That means the following thing, so I will maybe come back to that later on. That means the following thing. If you project, I mean, this is another way of saying the same thing. You can project the Gij over the Miyazawa-Janigan matrix and plot this as a function of Cij minus C bar ij. The theory says it should be proportional, it should be linear. And here you see the contacts. So Cij is 1, and this thing can be anything. And here you see the non-contacts, Cij is 0. And this difference can be pretty big if C bar is large. So, okay, so that means the following thing. So, if you look at your, so Gij is actually not really taking into account the true value of the energy. It tells you something differential between what you have in your particular structure you're interested in and what you would get from the competing structure, the competing structures. So that means, for instance, if a pair ij of amino acids here is in contact on your fold, but it's not in contact in the other ones, so this number is very close to 1, then it's very important that you get a very strong effective interaction between these two sites to maintain the right amino acid there and to maintain the contact. Okay? So you get a very strong effective interaction to have a good folding sequence. In the case where actually both numbers, so this one is 1 and this one is large, so that the difference is actually small, it doesn't matter what you put there, right? Because actually you can put something, I mean, you can put any kind of amino acid here. This is also something in the other fold, which is also in contact. So there is absolutely no pressure on this particular kind of sites, of pair of sites. So here you see something where the lambdas are negative, and that corresponds to the following thing. That corresponds to what people call negative design. So negative design means the following thing. You have a very strong correlation between amino acids along the sequence, not because they should be close to each other in space. They are not in contact. But actually, you want to prevent this particular sequence to fall into another structure where they would be in contact. So you have to make sure that the amino acids on these two sides are such that if they were in contact, they would have a very high energy. So this is a way to destabilize the competitor. And this is exactly what you see here. So these two things, negative design and positive design, put amino acids which have lower energy in order to maintain the contact, or put amino acids which would have high energy if they were in contact, are two ways which are known by people who actually built artificial proteins. And you can see that in the analysis here with the GIJB. And that corresponds to the two branches of these plots here. Okay. So one important thing here is that we find that the GIB are proportional to EAB. So is it true also in real data? I mean, is it true that the real GIJB that people infer from real data are proportional to the Miyazawa-Jerningham matrix? So we have looked at that. So this is the Miyazawa-Jerningham matrix, this 20 by 20 matrix, where, as I said, essentially people look at all amino acids on sites which are in contact and compute this kind of ratio. So you find, for instance, very strong values for between amino acids which are either, let's say, for instance, here they are negatively charged. So this is the aspartic and glutamic acids here. And here you see, for instance, positively charged amino acid, so arginine. And so you get very strong positive interaction in between plus and minus amino acids and very strong negative in between plus and minus, as you would expect. Here you see cysteine, which makes a very strong bond and so on. So now if you take many different protein families, infer the GIJB and do some kind of averages, well, I mean, some kind of correlation is found. So if you average the GIJB over all pairs of IJ in contact, you see some kind of correlation with that. And if you do the average in a slightly different way, which is actually more realistic, you find also larger correlations. But this correlation is very far away from 1. That means the following thing. That means it's certainly true that the GIJB which are inferred reflect the basic phenomenon of physical interactions, but they are also very highly effective. So they are really influenced by the background, the other amino acids. So there are free body interactions and so on, which are not taken into account here in these pairwise models. So the pairwise interaction try to adapt themselves to fit this as best as they can. So it's far away from being an exact model. Okay? But there is some kind of signal. Okay, so so just to finish on the story of competition between the structures. So what we can do, and we show, and this is the last thing I'm going to say. So you can rank, given a particular fold you are interested in, you can compute all these numbers and rank the other structures according to these numbers. And you can take the one with the highest W. Maybe this highest W will be 10 to the minus 2, something like that. So that's the most dangerous competitor, right? So for this particular structure, SB, which is here, actually the structure with the highest score is this one. And in fact, if you look at it, you see that many pairs of sites which are in contact here are also in contact on this one. So that means that in order to constrain a sequence to fall onto this structure rather than this one, you have to be very careful and do some fine-tuning. And all the GIJB we see, for instance, are related to this fine-tuning. So for instance, if you look at the center of the cube, you see it's contact in 9, 27, 23, 15, and so on. And it has a lot of contacts which are exactly the same here. So that's why actually the correlation between the amino acid, the GIJB we find here, it will be very weak because the CI minus C bar IJ will be very low, okay? So it will be very difficult actually to find the contacts between this site 4 and the other ones here, simply because actually it's in contact in the native fold, but also in the other one. So there is no correlation which comes from this particular, from the multi-sequence alignment associated to this structure. And in fact, if we remember how we predict the structure as a function of the top scores, it was perfect and then it failed. And actually the contacts which are missing are exactly these ones because they are associated to very weak couplings. So very weak couplings doesn't mean that there is no data here. It means simply that what we measure is not only a property of a native fold, it's a property also of the other folds. Okay, so that's something that was not totally clear also in the literature. Okay, so I'd like to finish on one aspect, which is the generative aspect. And I will show you what we find on lattice proteins and also some experiments. So the question is the following. Is the models which is inferred generative? So can you use it to generate new sequences? Are they good sequences? So it's very easy to test with lattice proteins. So what you can do is the following. So again, pick up one structure, generate some data, infer the corresponding POTS model. Now simulate the POTS model and generate new sequences. And you can test whether they actually fold into the same structure as the native one, or they don't fall, or they fall into something else. Okay? And so this is the outcome, for instance, for one particular structure, but this is very typical of the other ones also. So here I'm showing, with this procedure, what is the probability that the generated sequences fold into the same structure as the native one, which was used to generate the sequences from which the model was inferred. So this is kind of strange plot, but I mean, this is a way to increase the close to 1 probability of folding and condense the close to 0, okay? But you can see what's going on. So, and here, I have a measure of the diversity of the sequences which are generated, and it's a very crude measure. We should use entropy or something like that. I'll come to entropy, but this is a way that people use in the field, which is take what they call the consensus sequence. So when you look at your sequence, you have your alignment. On each column, you can look at the amino acid which is the most frequent one. That you call the consensus sequence, the consensus amino acid. Then you get the consensus sequence. And you can measure the distance of any sequence to this consensus. Okay? Tells you how mutation away you are from the consensus one. Okay, so it's a number between 0 and 27. So the data are the black dots that you can see here. So they are typically away about 20 mutations away from the consensus. That is very diverse sequences. They are far away from each other. And you get probability of folding which is above 0.99. In fact, the Monte Carlo simulation was done to ensure at least 0.99. Okay, but some of them are close to 0.999. Okay, these are the data. Now you can use simple algorithm to infer a model and generate new sequences, okay, and see whether they fall or not. So let's look at the green one. So the green one is a very simple algorithm which does the following thing. You have your data, and now find the model with maximum entropy which reproduces the 1-point statistics. So essentially that means the following thing. That means that on each site you compute the frequencies of each amino acid, and you compute the corresponding fields. No couplings at all the couplings are 0, and generate new sequences according to that. So independent site model. If you do that, the sequences you will generate will have the right 1-point statistics, but they will be completely wrong in the 2-point statistic, right? And they perform very badly. The probability that they fall is actually, for many of them, is actually very low. You see, they have a probability, this is the one standard deviation, of falling between 0.1 and 0.5. I mean, there is some signal, because the 1-point statistic is very important, but clearly it's not sufficient to fold with high probability. And now you can use other algorithms. So this is the cluster expansion algorithm I mentioned very briefly. And you can generate new data. So you use that to infer the couplings, and you generate new data. And you see that these sequences fall with high probability. Some of them are pretty bad sometimes, but many are actually a probability which is comparable to the one in the data. Okay. So it seems that the 2-point correlations are sufficient if you reproduce them to actually ensure folding. So this is something similar here. You can show what is for all the sequences which were generated. You can look at the true energy, which is minus beta log of probability of folding from the true model, compared to the energy of the Hamiltonian you have inferred. You see clearly some kind of monotonous relation. But there are a few things to notice. One, or maybe more, is that very high energy in the POTS model. Here you see about, if you go to above 20 or something, there seems to be quite uncorrelated with the energy of the true energy. That means all these sequences here, they are extremely bad. They have very high true energies, okay? And the POTS model has difficulty to actually fit the tails here. When you have a probability over sequences here with very low tails, so the way you fit the tails, it won't be very precise. But the POTS model is correct in saying that actually there should be high energy, but the precise value of energy is wrong. Okay. So there are bad sequences, but how bad they are is not really well predicted. And you see clearly a correlation here. And also here, the point is that the true energy, so you can see also variation here. I mean, the effective slope here varies a lot with the energy. And in fact, the slope is close to 1 in the region where you have most sequences. So essentially, it adapts to the region where you have most data. Okay, so just a few words I would like to add about the entropies, and then I'll go to the experimental data. So the kind of so the Potts model we infer, we can actually estimate with some techniques the entropy of a Potts model, and it will be a proxy for the entropy of a corresponding family. That is not true in the sense that reproducing the 1 point over 2 point statistics is important, but there are higher order statistics that we do not reproduce, so that means the entropy we estimate is certainly an upper bound to the true entropy. There are more constraints which are not taken into account. So these are the entropies which can be estimated for different families, so 4 different folds. These are the entropies in natural logs. I will come to powers of 10 in one slide, or maybe I can show that now. And then I'll come back to the other numbers. So again, this is the same picture as before, but now I can put numbers. So in this protein world, lattice protein world, these are the numbers. There are 20 to the 27, that is 10 to the 35 sequences. There are 10 to the 5 families. According to the entropy computed from the Potts model, which is some kind of upper bound, the number of sequences per family, that is the size of these blobs here, where a family means p naught larger than 0.99, is ranging between 10 to the 22 and 10 to the 25, depending on family. Some ones are bigger, other ones are smaller. And that's a problem that people have been interested in for a long time. Designability. Why are some structures or so particularly designable compared to other ones? So I will show you some work by Shaknovitz where he looked at this problem. Now, if you sum up this thing, if you multiply the number of families by the number of good folders, you get to a total number which is 10 to the 30 at most. That means the number of proteins or sequences which actually don't fall in any family is exactly or almost the same as the total number of proteins. I mean, most sequences do nothing, and a very tiny fraction of them will fold in 1 over 10 to the 5 families. And that, so there are just ridiculous lattice proteins, is pretty much a very good approximation of reality that people actually think in the field. And you see a huge diversity of sequences. And only a very tiny fraction of them was sampled by our Monte Carlo thing. So just one remark before I go to the to the data, is that this issue of designability or estimating the entropy has been an interesting point in the field for a long time. And I just want to mention one paper by Shaknovitz and England from 2003, where they had a very simple approximation of that. So they did not compute any entropy, any Potts model, whatever. But they had a simple approximation to estimate how designable is a family, that is, what is the entropy of this family. And what they did was very simple. They just looked at the contact map and they diagonalized it. And they said that the larger the top eigenvalue of this contact map, the more designable the corresponding family is. So we know that this cannot be true exactly, right? Because we know that the entropy is a function of a Jij, which depends on the competing structure. It cannot be a property of a single, family we are looking at. So, but anyway, it seems to be correlated. You see that smaller eigenvalues here correspond to smaller entropies and larger one to larger entropies. So I just want to mention briefly how I understand the paper, because I think it was an interesting one. So what they did is the following. They look at the energy of one particular sequence in one particular structure. So the Cij is the Cij of this particular fold. And that you can write, so this is the formula I mentioned before, but you can rewrite by using some spins. So there is no AB here, sorry, it's a mistake. And the spins are 0, 1. It tells you whether you have amino acid A on side I, this is 1, or you get 0. Okay? Now you can start a very crude approximation, saying that instead of having 0, 1 spins, let's say there are, Gaussian spins, in the sense that I use that as a quadratic form for my Gaussian measure. Then in that case, within this very crude approximation, the partition function will be simply the determinant of some identity matrix which fixes the fact that actually this kind of constraint, let's say sigma squared, well, I mean, it's normalized, but anyway, they have some Lagrange multiplier for this kind of constraints. And then they have to diagonalize this matrix here, which is just the product of C in the side space and E in the amino acid space. Okay. Now, if you are interested in very good folders, you are interested in sequences with very low energies. So what you would like to see is how the entropy is a function of the energy. Since the temperature beta is here, you can compute the entropy and the energy as a function of beta, and then in a parametric way, you get this S as a function of E. So in the very high beta regime here, that is very low E, the partition function can be estimated only from the maximal eigenvalues of E and C. And in particular, if you do a calculation, which is elementary, you see that at very low E, you get a linear relation between S of E and E, between the entropy of energy, and the slope is 1 over the top eigenvalue of the correlation matrix, times something which is the constant. It does not depend on the correlation matrix, right? That means when this correlation matrix has a very large eigenvalue, then the slope is smaller, it's flatter. When it's a very small top eigenvalue, then it's steeper. So obviously, if the slope is smaller, you can think that maybe you can go to lower E's. So you can find sequences with better and better energies in terms of lower energies. So this corresponding structure would be more designable. So that was the intuition behind the paper, as I understand. So this is essentially true, so actually it's a bit more complicated than that, but it's a good approximation. Okay, so I will finish now on experimental results. So I will present results which are already 10 years old, but there are more recent results which I can briefly talk about. So this idea of using sequence statistics to generate new or to design new sequences was introduced a long time ago, and in particular in this paper by Rama Ranganathan in 2005. So he looked at the WW domain I mentioned last week, if you remember, which is a small binding unit of about 30-something amino acids. And let me tell you what he did, because I think it was a very nice way of solving the problem without actually inferring explicitly the Gij, but doing something very similar. So what he did was the following. So he considered first a case where we can generate artificial sequences which respect only the one-point statistics on each side. They are not supposed to be interesting, but it's a way to see they are not interesting, right? So it's a kind of null model. So he started from the sequence data. So you start from, this is your alignment. And what you can do is to do random reshuffling on each column. You can reshuffle the lines on each column. Obviously, if you do that, independently of the other columns, the statistics, the frequency of each amino acid on each column will be kept unchanged. But you will generate completely new sequences, right, where you have destroyed any kind of correlations. So that's a way to generate new sequences. That is very easy. The more interesting case is this one. How do we generate new sequences which keep the first order statistics on each column and also the pair correlations? So one way to do that, which I've explained, is to compute the couplings, do a Monte Carlo on the Potts model, and you generate this kind of. But he didn't have inference technique, so this is what he did. Start from your multi-sequence alignment and do exactly the same step as here, but then define an energy. So what you compute, the energy, is the sum over all I and j, A and B, of the Fij AB minus the Fij AB in the data squared. So it's a very empirical thing. So from your data, from a multi-sequence alignment, you compute the 2-point statistics here and just memorize it somewhere, store it in your computer. Now, when you do this kind of elementary operation, okay, you change the 2-point statistics. The Fij will be different. Don't care about the Fia, it's always unchanged. So you can compute this thing here, and this you call the energy of this particular reshuffle alignment. Okay? And now do Monte Carlo at an inverse temperature T, which is a fake temperature that you take not too large. So in principle, this is a way to solve the maximum entropy problem, because the only thing you impose here is that Fijb of your data is the same as the one that you generate with your artificial sequences, right? And if you add these only constraints, then you are most likely to find a distribution of the sequences which is the one of maximum entropy, right? So this is a very nice way to solve the problem without inferring any GIJB. Except that it doesn't work so well in the sense that it gets stuck. You know, the Monte Carlo is very slow, and so it's not a perfect solution, but it's a very clever one. Okay, so what was the outcome of these things here? So it generated a certain number of sequences here, which is not too large, but actually it was a long time ago. I mean, 13 years ago. So experimental techniques were not as good as now. And you could see whether these sequences, so these are natural sequences, 42 sequences from the multi-sequence alignment from different organisms. You generate 43 sequences with this technique, 43 with this one, and 19 which were just random, which were taken from a very simple model where you just compute the background frequency of all amino acids independently of a site and generate something purely random. And so what is now, so this thing here is a control. So depending on how the experiment is done and so on, you would expect that if you had a perfect experiment, all natural sequences should fold, should be soluble, okay? Everything should be nice. But of course, the experiment is not perfect. And you see only 2/3 of the natural sequences actually fold or are detected as folded and soluble and so on in the experiments. So it tells you you should compare your result to that, okay? Now, if you use sequences which were generated only by respecting the 1-point statistic, you get this kind of things. None of them actually folded among the 43 ones generated. The random one, you get essentially the same thing. They are a bit more soluble here than this one. I mean, they don't aggregate in water, but it's not very much dramatic. While about 30% of this one, which were generated with this much more sophisticated procedure, actually could be seen as folded. So that means respecting only the 2-point statistics was sufficient to make them fold, at least 30% of them. In fact, he did more than that. Ranganathan did more than that. He looked actually, he determined the structure, 3D structure of these artificial sequences, which are far away from any known natural sequence. And you could see that compared to this one, which is known one, natural one, see essentially the same 3D structure. So not only they fold, but they fall into the right structure. So can we actually relate the fact that some of them fold among these among these 43 here? You have 30% of them which fold, and 70% which don't do anything. Can we be a little bit more quantitative and see how it's correlated to the energy of the Potts model? So this is what I'm going to show, and then I will stop. So just one remark before I show that, because I should have shown this before. When you do the inference, actually, you can. So the inference of the GIJB, HIA of A, and so on should reproduce. It says that the 1-point statistics and the 2-point statistics should be reproduced. Okay, so that's just a measure of quality here. It's interesting to see that this Potts model is also able to reproduce the 3-point statistics. Okay, so it's not trained to do that. Okay, so that means the 3-body couplings, though they exist, are not very strong. Okay, that's something which should be better understood. There is something, because now this is the joint probability for 3 amino acids. If you do the connected correlation, you can see some deviation, right? They are not perfectly aligned, but they are pretty small. Okay, that was just an aside remark. So now, just to finish, I take the sequences generated by Rama Ranganathan, either the one which respects the pairwise correlations, pairwise statistics, the one which respects only the 1 point, and these are the natural sequences. Now what you can do is put this as vertical bar. Yes, each vertical bar is a sequence, and here you have the energy computed with the Potts model, which is inferred from the data. So you see that the natural sequences have on average smaller energies, lower energies, while the independent one have higher energies, and the one which are generated with the pairwise procedure and when you respect the pairwise correlation, have intermediate energies. Now in gray, you see the one which fold, and in red the one which, no, in gray the one which do not fold, and in red the one which fold. So you see the one which fold, apart from this one, are essentially one among the CC class, the one which respected the pairwise statistics, with lowest energy. So that means that it's not, it's certainly true, it seems to be true that if you take into account only the pairwise statistics, you can have a model which allow you to generate sequences. And the sequences that you find with the, which are in the bottom part of this histogram here, that's a histogram of all sequences you can generate, seems to be good. They have energies which are comparable to the natural one. If you randomly sample from that, there is a good probability, you don't know. I mean, there is a good probability that the energy will be large and it won't fold. But if you sample from this part, it's much higher probability. So that I don't understand, okay, in the sense that we have some kind of strange result here where on one side, pairwise interaction seems to be sufficient to generate good sequences. On the other side, you have to look at the bottom part of the spectrum of the energies to increase the probability that there are good sequences. You should not sample from temperature 1, because then, and that's something we see on much more recent data on a much bigger protein, because this one is only 30 amino acids, so you can criticize, I mean, in the sense that it doesn't take many good combination to get the fold, but on much bigger one with hundreds of amino acids, you see exactly the same thing. So it seems that these pairwise models capture something very essential if you go to low enough temperature. Okay, so I must say I do not understand why exactly, but it seems to be true. So I think I will stop here for today. I wanted to finish on this experimental data.
So, other questions? Let me warn that Rémi is not staying for lunch today, so if you have questions, it's now.
Don't take it personally, I have to go. But I will be there next week, obviously.
No questions? Well, there will still be a lunch, but it will be lunch without the speaker this time, so in 10 minutes.